For most of human history, the universe seemed to hold limitless possibilities. We looked up at the night sky, a vast and dark canvas dotted with distant points of light, and imagined journeys without end. There were no known rules governing how fast one could travel across this cosmic ocean. If you could build a powerful enough engine, you could go faster and faster, indefinitely. The only limits were those of our own engineering and imagination. This was a universe of pure, unbridled potential. A playground for thought experiments and dreams of interstellar empires built on the back of ever-increasing speed. It was a simple, intuitive idea that resonated deeply with our pioneering spirit. This belief in infinite velocity was not just a fanciful notion, it was the default assumption for centuries. From the horse-drawn cart to the steam locomotive, every new invention pushed the boundaries of speed, suggesting that this trend would continue forever. The cosmos, we thought, was a grand open road. There were no cosmic traffic cops, no universal speed limit signs posted between the stars. The journey from one galaxy to another was simply a matter of time and technological prowess. We envisioned starships accelerating continuously, eventually reaching speeds that would make the vast distances of space manageable within a human lifetime. The universe was ours for the taking, if only we could go fast enough. But nature often has surprises in store, hiding its most profound secrets in plain sight. The universe, it turns out, does have rules. They are elegant, subtle, and often counterintuitive to our everyday experience. The clues were there, hidden within the behavior of light and energy, waiting for a mind bold enough to piece them together. The quest to understand the nature of light itself would ultimately lead us to an invisible wall, a fundamental barrier woven into the very fabric of space-time. This barrier would redefine our place in the cosmos and reshape our dreams of exploration, forcing us to think more creatively than ever before. The stage was set for a revolution in our understanding of reality. It would take a brilliant flash of insight at the dawn of the 20th century to reveal this ultimate cosmic law. Before this revelation, the notion of a universal speed limit would have sounded like science fiction, a strange and arbitrary rule imposed upon a limitless cosmos. Yet, this very rule would become one of the most tested and confirmed principles in all of science. The idea of a universe without a speed limit was about to be shattered, replaced by a new, more intricate, and far more fascinating picture of the cosmos we call home. Then came Albert Einstein. He was not a starship captain or an engineer, but a patent clerk with a mind that soared through the cosmos. In 1905, with his theory of special relativity, he introduced a radical new concept to the world. He proposed that there is, in fact, a speed limit in the universe. It is not a limit we can engineer our way around or push through with brute force. It is an absolute fundamental property of space-time itself. This ultimate speed is the speed of light in a vacuum, traveling at an astonishing 299,792,458 meters per second. This isn't just how fast light happens to travel, it's the fastest that anything, any information, any cause, can travel from one point to another. Imagine light as the supreme messenger of the cosmos. Nothing can outrun it. This cosmic speed limit, often represented by the letter C, is the universe's ultimate law of the road. It governs the relationship between space and time, energy and matter. Einstein showed that as an object with mass approaches the speed of light, strange things begin to happen. Time for that object slows down relative to a stationary observer, and its mass increases. These are not just theoretical quirks, they are measurable effects that have been confirmed in particle accelerators around the world. The speed of light is more than just a velocity. It is the bedrock upon which our modern understanding of physics is built. This concept was a profound departure from the classical physics of Isaac Newton. In Newton's universe, time was absolute, flowing at the same rate for everyone, everywhere. Space was a static stage upon which the events of the cosmos played out. But Einstein revealed a more dynamic and interconnected reality. He unified space and time into a single, four-dimensional continuum called space-time. In this framework, the speed of light is the constant that links them together. It is the same for all observers, no matter how fast they are moving. This simple but powerful postulate is the source of all the mind-bending consequences of relativity. So, the universe does have a speed limit, and it is woven into its very essence. It's not a frustrating barrier, but a fundamental principle that makes the cosmos coherent and predictable. It dictates how stars shine, how galaxies form, and how the universe itself evolves. It tells us that we cannot simply hop in a spaceship and zip across the galaxy in an afternoon. The cosmic speed limit forces us to confront the true scale of the universe and inspires us to seek new, more ingenious ways to explore it. The journey to the stars would not be a simple sprint, but a challenge that demands a deeper understanding of the laws of nature. To grasp the sheer magnitude of the cosmic speed limit, let's stage a hypothetical race to the Moon. Our finish line is the lunar surface, approximately 384,400 kilometers away from Earth. Our first contestant is light itself. The moment we start the race, a pulse of light leaves Earth and travels through the vacuum of space. It crosses the vast distance in just about 1.3 seconds. Before you can even finish reading this sentence, light has already reached the Moon. It's an almost instantaneous journey on this scale, a testament to its incredible velocity. This is the undisputed champion, the gold standard of cosmic speed against which all others are measured. Now, let's consider our other racers. An electron, one of the fastest subatomic particles we can accelerate, can be pushed to incredible speeds in a particle accelerator, say 99.99% of the speed of light. Even at this breathtaking pace, it would still arrive a fraction of a moment after the light pulse. It can get tantalizingly close, but it can never quite win the race. Next up is a spacecraft, like the Space Shuttle, which traveled at about 28,000 kilometers per hour in orbit. At that speed, the journey to the Moon would take nearly 14 hours. This is a significant improvement over older technologies, but it's a leisurely stroll compared to the sprint of light. Let's slow things down even further to bring the scale into human terms. Imagine driving a car at a steady 100 kilometers per hour. If there were a road to the Moon, it would take you about 3,844 hours, or roughly 160 days, to get there without stopping for gas or rest. That's more than 5 months of continuous driving. The journey transforms from a quick trip into a significant life event. And what about a person walking? At a brisk pace of 5 kilometers per hour, it would take you over 76,000 hours, or nearly 9 years, to walk to the Moon. This thought experiment beautifully illustrates the immense gap between our everyday speeds and the ultimate speed of the cosmos. The differences are staggering. From the blink of an eye journey of light to the multi-year trek of a walker, the Moon provides a perfect backdrop to appreciate what the cosmic speed limit truly means. It's not just a little bit faster than everything else, it's in a completely different category of existence. This comparison highlights the immense challenge of interstellar travel. The nearest star, Proxima Centauri, is about 4.2 light-years away. If it takes light over 4 years to get there, our current technology would require tens of thousands of years for the same journey. The cosmic speed limit defines the vast, empty chasm between the stars. So why can't we just build a better engine and push an object with mass, like a spaceship or even a single atom, to the speed of light? The answer lies in one of the most famous equations in all of science, E equals mc squared. This equation, also from Einstein, reveals a deep and fundamental connection between energy and mass. It tells us that mass is a form of concentrated energy. It also tells us that to make something go faster, you need to give it more kinetic energy. But here's the catch from special relativity. As an object's speed increases, its effective mass, or what we call relativistic mass, also increases. Think of it like this. As you push a spaceship closer and closer to the speed of light, it gets heavier and harder to push. At everyday speeds, this increase in mass is so tiny that it's completely unnoticeable. But as you approach C, the effect becomes dramatic. The energy you pour into accelerating the ship is increasingly converted into mass rather than speed. This means you need more and more fuel to get smaller and smaller gains in velocity. It's a law of diminishing returns written into the fabric of the universe, a cosmic headwind that grows stronger the faster you go. As you get infinitely close to the speed of light, the energy required to go any faster approaches infinity. To reach the speed of light itself, an object with mass would require an infinite amount of energy, which is more energy than exists in the entire observable universe. This is the ultimate barrier. It's why particles with mass, from electrons to starships, are forever relegated to the slow lane, while only massless particles like photons, the particles of light, can travel at the cosmic speed limit. Photons have no rest mass, so they are born traveling at speed c, and will always travel at that speed in a vacuum. This principle is not just a theoretical curiosity, it's a daily reality for physicists working with particle accelerators like the Large Hadron Collider. They pump enormous amounts of energy into tiny protons, accelerating them to 99.9999991% of the speed of light. But no matter how much more energy they add, they can only get those protons incrementally closer to CF. They can never reach it. The burden of mass is a fundamental law. To break the light speed barrier, we can't just try to push harder. We have to rethink the very nature of motion itself and find a way to sidestep this cosmic rule. Our experience of motion and energy is, well, profoundly shaped by the environment we live in. Here on Earth, we're constantly under the influence of gravity. This relentless force pulls everything towards the planet's center, creating a high-energy, high-density environment. When we try to move, we're not just pushing against air resistance, we're constantly fighting gravity's pull. Think about launching a rocket. It requires an immense amount of energy just to escape Earth's gravitational well. This constant struggle against gravity compresses and contains energy, making high speeds difficult and, honestly, pretty costly to achieve. But in the vacuum of space, far from any significant gravitational source like a planet or a star, the situation is completely different. Space is a low-density, low-energy environment. Once a spacecraft escapes Earth's gravity, it can coast through the void with its engines off, maintaining its velocity almost indefinitely due to inertia. There's virtually no friction to slow it down. This is why probes like Voyager 1, launched in 1977, are still traveling through interstellar space decades later. In the emptiness of space, energy used for propulsion is far more efficient at creating and sustaining speed than it is here on Earth. The grip of gravity does more than just make liftoff difficult. It warps space-time itself, as described by Einstein's theory of general relativity. A massive object like Earth creates a dent in the fabric of space-time, and this curvature is what we experience as gravity. This warping can even affect the path of light, a phenomenon known as gravitational lensing. While this effect is subtle near Earth, it becomes significant near massive objects like stars and black holes. Gravity, therefore, not only anchors us physically, but also influences the very stage upon which cosmic events unfold, altering the rules of motion in its vicinity. Understanding this difference between a high-gravity environment and the vacuum of space is, well, crucial. On Earth, our intuition about speed and energy is skewed by the constant need to overcome resistance. In space, the primary challenge is not friction, but the vast distances and the limitations imposed by the speed of light. To truly envision interstellar travel, we must shed our earthbound intuition. We have to think in terms of the physics of the void, where energy and motion behave in purer, more direct ways, and where the fundamental properties of space itself become the next great frontier to explore. Section 6. The Fabric of Space-Time Unveiling Hidden Layers. For a long time, we pictured space as a simple, empty void, a black, featureless backdrop for the planets and stars. But modern physics, particularly ideas emerging from quantum mechanics, suggest that space is far more complex and dynamic. One intriguing idea, which we can call quantum physics theory for our exploration, proposes that what we perceive as empty space is not empty at all. Instead, it might be a roiling sea of energy, a quantum foam of particles and antiparticles popping in and out of existence on incredibly tiny scales. This suggests that space-time itself might have a texture, a structure, with different properties at different levels. Imagine space-time not as a smooth sheet of fabric, but as a multi-layered material. The layer we experience, the one governed by Einstein's relativity, is just the surface. On this surface, the speed of light is the absolute limit. But what if there are deeper layers, other strata of space-time with different physical properties? This is a speculative but exciting frontier of theoretical physics. If space has these hidden dimensions or layers, it's possible they possess different characteristics, such as a lower density or a different relationship between energy and resistance to motion. It's like discovering that the ocean has different currents at different depths. This concept of a structured vacuum opens up mind-bending possibilities. If different layers of space have different properties, could the cosmic speed limit be a property of our specific layer only? Perhaps the constant c is not a universal constant for all of reality, but a local bylaw for our observable universe. Traveling through a different, less dense layer of space-time might not be about accelerating a physical object through our space, but about shifting the object into a different state of existence where the rules of motion are fundamentally altered. This is a profound shift from thinking about propulsion to thinking about navigation through the very fabric of reality. Exploring these ideas requires us to merge our two great pillars of modern physics: general relativity, which describes the large-scale universe of gravity and space-time, and quantum mechanics, which governs the bizarre world of the very small. Currently, these two theories don't fully agree, but in the search for a unified theory of everything, physicists are exploring concepts like string theory and quantum loop gravity. These theories hint at a universe far stranger and more wonderful than we can imagine, a universe where the vacuum of space is the most interesting and mysterious place of all, holding the keys to our cosmic future. Section 7. Navigating the quantum foam. A new path forward. If space does have these hidden layers or a quantum texture, how could we possibly use them to travel faster than light? The idea isn't to break the speed of light in our layer of space-time, as that seems impossible. Instead, the goal would be to find a way to bypass it. Imagine our universe is like a large flat piece of paper. To get from one point to another, you have to travel across the surface. But what if you could fold the paper, bringing the start and end points right next to each other? You could then punch a hole through the paper, creating a shortcut. This is the essence of a wormhole, a theoretical tunnel through space-time. This concept of manipulating space-time is the heart of several theoretical faster-than-light travel methods. The Alcubierre drive, for example, proposes a way to warp space around a starship. It would work by contracting the space in front of the ship and expanding the space behind it. The ship itself wouldn't be moving through space at incredible speeds. It would be sitting inside a warp bubble of space-time that is being moved. From inside the bubble, nothing would feel out of the ordinary. But to an outside observer, the bubble and the ship it contains would appear to travel faster than light, without ever locally breaking the cosmic speed limit. These ideas rely on the ability to interact with the fabric of space-time in ways we currently cannot. To create a wormhole or a warp bubble, we would likely need something called exotic matter, or negative energy density. This is a hypothetical form of matter with bizarre properties, such as repelling gravity instead of attracting it. While we have observed effects in quantum mechanics that mimic negative energy on a microscopic scale, we have no idea how to produce or stabilize it in the amounts needed for FTL travel. It remains one of the biggest hurdles between science fiction and science fact. However, the pursuit of these ideas forces us to ask deeper questions. If we could navigate the quantum foam, we might find ways to reduce the effective resistance of space-time itself. Perhaps we could create a slipstream at the quantum level, allowing a vessel to glide through a lower density layer of reality. This is no longer about building bigger rockets. It's about becoming masters of cosmic engineering, manipulating the fundamental constants of our universe. It's a daunting task, but it represents a potential path forward. A way to journey to the stars not by brute force, but by cosmic finesse. Section 8. Redefining propulsion energy in the void. The challenge of interstellar travel is twofold: the speed limit of light and the energy required to approach it. As we've seen, conventional propulsion, which involves pushing mass to create thrust, becomes incredibly inefficient as you near light speed. This forces us to redefine what propulsion means in the context of cosmic travel. If moving through space is the problem, perhaps we need to focus on how energy interacts with the vacuum of space itself. The vacuum is not empty. It's filled with quantum fields and zero-point energy. Could this be a source of energy for a new kind of propulsion? One speculative concept is the quantum vacuum thruster, which would theoretically push against the quantum foam of spacetime itself, rather than expelling propellant. It's an idea that borders on fiction, but it stems from a real observed phenomenon called the Casimir effect. This effect shows that two very close parallel plates in a vacuum will be pushed together by an imbalance in quantum fluctuations. While the force is incredibly tiny, it proves that the vacuum is not inert. Harnessing this energy is a monumental challenge, but it represents a complete paradigm shift in how we think about moving through space. Furthermore, if space has different layers with varying energy densities, as our quantum physics theory suggests, then propulsion might become a matter of energy state rather than kinetic motion. Instead of accelerating to a high speed, a ship might expend energy to shift into a different layer of space-time where travel is easier. In this lower density space, the same amount of propulsion energy might result in a much greater effective velocity. The energy wouldn't be used to increase kinetic motion in our familiar sense, but to change the ship's relationship with the fabric of reality itself, allowing it to glide along a path of least resistance. The speed of light, CE, would remain a constant within any given layer of space-time. It is the law. But the energy required to move from point A to point B could be drastically different depending on the path you take through the layers of space-time. This reframes the problem entirely. We are no longer just trying to build a faster engine. We are trying to become cosmic cartographers, mapping the hidden geographies of space-time to find the most energy-efficient routes. Our future in space may depend less on the power of our thrusters and more on our understanding of the fundamental nature of the void. Section 9. Beyond the Horizon, a New Cosmic Journey. For millennia we have stared at the stars and dreamed of reaching them. The discovery of the cosmic speed limit seemed at first to place those dreams forever out of reach, locking us within our own solar system. The vast distances of interstellar space, measured in light years, appeared as insurmountable gulfs. But science does not end with the discovery of a barrier, it begins. The speed limit of light is not an end to the story of exploration, but a challenge to our ingenuity, a call to think bigger, deeper, and more creatively than ever before. It forces us to move beyond our classical, intuitive notions of travel. The path to the stars may not be a straight line traveled at ever-increasing speeds. It may instead involve a profound shift in our understanding of reality. The journey requires us to rethink space itself, not as an empty stage, but as a dynamic, complex, and multi-layered medium. The true frontier is not just the physical space between stars, but the theoretical space of new physical laws. By exploring the quantum nature of the vacuum and the hidden geometry of space-time, we might discover new modes of travel that today seem like magic, just as flying would have seemed to our distant ancestors. Let your imagination wander. Picture a future where starships don't blast through space but navigate its currents, folding space-time to connect distant worlds in an instant. Imagine vessels that shift between layers of reality to find faster routes, powered not by chemical rockets but by the energy of the vacuum itself. This is the new dream of interstellar travel, a dream born not from defying the laws of physics, but from understanding them on a much deeper level. It's a journey that begins in the mind, with the courage to ask what if, and the persistence to search for the answers. The universe is full of wonders, and the greatest of these may be the laws that govern it. The cosmic speed limit is one such wonder. It defines our universe, and in doing so, challenges us to become something more than we are. It beckons us to look beyond the horizon of our current knowledge and to embark on a new kind of voyage, a journey into the very fabric of the cosmos. The stars are waiting, and while we may never outrun a beam of light, we might just learn to take a shortcut through the beautiful, mysterious, and boundless universe we call home.
For over a century, physics has been governed by one beautiful, unyielding rule. It comes from Albert Einstein's brilliant mind. He told us that there is a cosmic speed limit, a maximum velocity that nothing in the universe can exceed. This ultimate speed is the speed of light. Imagine a beam of light, a photon, racing across the void. It travels at an astonishing 186,000 miles every single second. This isn't just a suggestion, it's a fundamental law of nature. It's the universe's ultimate highway speed, and everything with mass is destined to travel in the slower lanes, forever chasing a speed it can never reach. Why is this speed limit so absolute? Einstein's theory of special relativity explains it with profound elegance. As an object with mass, like a spaceship or even a tiny particle, begins to accelerate, its mass increases. The faster you go, the heavier you get. This effect is minuscule at the speeds we experience on Earth, but as you approach the speed of light, your mass starts to grow exponentially. To reach the speed of light itself, your mass would become infinite. Pushing an object with infinite mass would require an infinite amount of energy, which is more energy than exists in the entire observable universe. Think about the most powerful rockets we can build today. They burn incredible amounts of fuel just to escape Earth's gravity and drift through our solar system. Even our fastest probes, traveling for decades, are moving at a tiny fraction of light speed. The Voyager 1 spacecraft, our farthest messenger, travels at about 38,000 miles per hour. That sounds fast, but light could circle the Earth more than 7 times in the blink of an eye. The vast distances between stars make interstellar travel seem like an impossible dream, a journey that would take tens of thousands of years, all because of this unbreakable light barrier. So the dream of zipping between galaxies, of visiting alien worlds in a single lifetime, seems to be a fantasy. Traditional physics, the very framework that allows us to understand the cosmos, puts up a giant "do not exceed" sign at 186,000 miles per second. It tells us that no matter how advanced our engines become, no matter how much fuel we burn, we are fundamentally stuck. We are inhabitants of a cosmic neighborhood, with the rest of the universe locked away behind an impassable barrier of time and distance. But what if we've been looking at the problem from the wrong angle? What if the secret isn't to go faster, but to change the road itself? Let's imagine a different way of thinking about the cosmos. This is where a new idea, let's call it quanta physics, comes into play. This theoretical framework starts with a radical proposition. What if the vacuum of space isn't truly empty? We often picture space as a vast, black nothingness, a passive stage where planets, stars, and galaxies perform their cosmic dance. But quantum physics suggests that space itself is a dynamic, tangible medium. It's a fabric woven from the fundamental energy of the universe, something that can be stretched, compressed, and manipulated, much like a sheet of rubber. This idea changes everything. If space is not a void but a substance, then it might have properties we are only beginning to understand. Think of it like water. A fish swims through water, but the water itself can flow, form currents, and create whirlpools. In this new view, space is not just the where, but also the how of movement. Quantum physics proposes that this quantum foam of space-time is filled with latent energy. This energy doesn't just sit there, it holds the potential to be shaped and molded if we can figure out how to interact with it on a fundamental level. How would one go about shaping space? According to this theory, the key lies in the relationship between energy and gravity. We know from Einstein that massive objects like stars and planets warp the space-time around them. This warping is what we experience as gravity. It's a gentle, large-scale curvature. Quantum physics speculates that by using immense concentrated bursts of energy, we could create highly localized and intense gravitational fields. These fields wouldn't just gently curve space, they could actively reshape it, creating temporary tunnels or corridors with entirely different physical properties. This is a profound departure from our classical understanding. We are no longer just passengers traveling through a static universe. Instead, we become cosmic architects, capable of altering the very medium we travel through. The challenge, of course, is monumental. It would require a mastery of energy far beyond our current capabilities, a way to generate and control forces on a scale that could influence the fabric of reality itself. But the concept opens a door that was once firmly shut, suggesting that the limitations of the universe might be more flexible than we ever imagined. The empty space between stars might just be the most interesting thing out there. So how does changing space allow a ship to break the light barrier? The trick is that the ship itself never actually moves faster than light within its local patch of space. It's a clever cosmic loophole. Imagine you are standing on a rug. To get to the other side, you could walk across it, or you could have someone grab the far end of the rug and pull it towards you. You haven't moved on the rug, but your position in the room has changed dramatically and quickly. This is the central idea of breaking the light speed limit with quantum physics. The spaceship stays still while the space around it does all the work. Let's put some numbers on this fantastic idea. In normal space, the top speed is a firm 186,000 miles per second. But inside one of these specially created corridors of altered spacetime, the rules are different. By using tremendous energy to manipulate gravity, a ship could compress the space in front of it and expand the space behind it. This creates a warp bubble. Inside this bubble, the ship is safe and stationary. But the bubble itself, carried along by the wave of contracting and expanding space-time, could move through the universe at an effective speed of, say, 511,500 miles per second, nearly 3 times the speed of light. This method completely redefines our use of energy and gravity. Traditional rockets use energy for propulsion, pushing the ship forward through brute force. In this new model, energy isn't used to push the ship, but to manipulate the gravitational field around it. Gravity is no longer just a force that pulls you towards a planet, it becomes a tool, a sculptor's chisel used to carve pathways through the cosmos. The ship's engines would be focused on generating and sustaining the warp bubble, a task requiring unimaginable power, but one that obeys a different set of physical principles than simple acceleration. This concept bears a strong resemblance to the warp drive seen in science fiction, like in Star Trek. However, there's a key difference. Many sci-fi depictions are vague about the mechanics, often treating it like a magical hyperdrive. Quantum physics, while theoretical, attempts to ground the idea in a plausible extension of our current understanding of physics. It doesn't ignore Einstein's laws, it finds a creative way to work around them. The ship never locally breaks the speed of light, so the paradoxes of time travel and infinite mass are avoided. It's a more disciplined, thoughtful approach to one of humanity's greatest dreams. Why does this idea, even as a far-off theory, matter so much? It represents a fundamental shift in our cosmic perspective. For all of human history, we have been bound to our home world, and more recently, to our solar system. The stars have been beautiful but unattainable points of light. The sheer scale of the universe has made us feel small and isolated. The possibility of faster-than-light travel, enabled by manipulating space-time itself, transforms us from passive observers into potential cosmic explorers. It turns the galaxy from an impossibly large ocean into a navigable sea, with new worlds and new discoveries waiting on distant shores. This concept ignites the imagination and fuels the scientific drive for discovery. It suggests that the answers to our biggest challenges might not lie in refining old technologies but in discovering entirely new physical principles. Exploring quantum physics would push us to understand the nature of dark energy, the mysterious force causing the universe to expand. It would force us to probe the relationship between gravity and quantum mechanics, one of the greatest unsolved problems in all of science. The pursuit of this knowledge, whether it leads to a warp drive or not, will undoubtedly unlock countless other secrets about how our universe works. Of course, the path forward is filled with enormous, unanswered questions. How much energy would it actually take to create and sustain a warp bubble? Current estimates suggest it might require the energy equivalent of an entire star, or perhaps even more. How could we generate and control such power without destroying the ship and everything around it? What exotic forms of matter or negative energy might be needed to make the theory work in practice? These are not small engineering problems. They are deep, fundamental questions that challenge the very limits of our scientific knowledge. Ultimately, the dream of warp speed is more than just a desire for faster travel. It is a reflection of our innate human curiosity, our unyielding desire to reach for what lies beyond the horizon. It's the same spirit that drove early navigators to cross oceans and astronauts to walk on the moon. While quantum physics and warp bubbles remain on the drawing board of theoretical science, they serve as a powerful inspiration. They remind us that the universe is vast and full of wonders, and that the most exciting discoveries may still be waiting for us, nestled in the very fabric of space and time.